The question is combination sum. Um, you are given an array of distinct integer and an target integer, and we have to return all the unique combination of candidates chosen to get the sum to target. You can choose combination in any order. The same number may be chosen unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen number is different. The test case are generated such that the number of unique combination that sum up to the target is less than 150 for the given input. Candidates 2, 3, 6, 7, target 7, output 2, 2, 3, 7. 2 and 3 are candidates. 2 to 3 sum up to 7, and 2 can be used multiple times, and 7 equal to 7. There are only two combinations. The for 2, 3, 5, and the target is 8. So this can be 2, 2, 2, 2, 2, 2, 3, sorry 2, 3, 3, and 3, 5. Similarly, for candidate 2 and target equal to 1, the output will be an empty array. So the approach here can be that first we can sort the input array so that we will get all the numbers in a sorted format, and we can start from the smallest integer, and like in subsequent so we can do like a depth first search, like a recursion approach we can take, and and before going into the depth of every recursion, we can add the current candidate item, like the current index, and then start at index 0. So we can add this index 0 to the current list of candidates, maintain return array. This can be the total output, right? And then candidate array. This can be the candidate array can be the array that we are maintaining throughout. So now like what we can do is we start at index 0, we can add candidate 0, and we can also have current sum, right? Candidate sum. So we can initialize candidate sum to be 0. So the reason why we should be sorting this is because if array or candidates of index, right, plus candidate sum is greater than target, then we can have an early condition of if this is true, then we can have an early condition of termination, early termination condition. Now if candidate sum, right, if candidate sum is equal to target, so basically if candidate sum is equal to target, then we can, and then we can append then we can make a copy of candidate array and append that to so with list we can initialize a new array, and we can put candidate array in this, and then right, finally after this step we can return. Now in like this can be the normal scenario. uh, for this one we can always iterate for I in range index. So we will always start with the, so there are two things. First of all, we will always, if we are at an index 0 in the depth first search, we'll always also begin at index 0 itself, because if we are at 2 in this scenario, right, 2 3 5 2 2 2 2 is a valid solution. So we will keep adding 2 till we reach yeah, so that we can reach the target. And then this can be length of input, this can be candidates, and yeah, so basically this is there. Otherwise what we can do is we can candidate array dot append right, this can be one thing. Another thing is just called DFS here. This can be again, so we are calling, let us make this function definition to include index and sum, right? So we can call at this, we can call this as index itself at I, sorry, and like this is the current index, and finally we can have sum plus candidates I. Now this is like an important step for backtracking that we will finally need to pop. So yeah, this is essentially the important step for recursion, that if we add I, we will need to pop this, and then essentially, so essentially what you can notice is that for all of this recursion we are utilizing only one array, right? And essentially we will just keep adding index, like we will just keep adding elements to that and maintaining the sum. And like whenever we return, we will call a new like value. So yeah, finally we can, in the outer loop we can just call DFS with 0 index and 0 sum, and then return return array. So yeah, this is the pseudocode. Let's go to the coding now. The constraint here that we have is that candidate length is 1 to 30, so we don't have any invalid cases, and the candidate I is equal to 2 to 40. So here we can describe the depth first approach, right? So because we have a depth first approach, we can like every candidate can be included in the array, right? So basically if there is like a array of say size n, then every candidate can be included target divided by, so if you take the worst time case complexity, every number can be included by target divided by the minimum number, right? And essentially so this will have exponential complexity for sure, because this is like a recursive solution, and the depth of the stack will be also order of n, and then essentially the depth of the stack will be order of like order of target actually, and one number can be, and like this will be like n raised to, essentially n raised to m kind of a solution, where n is the number of elements and m is the maximum depth of the stack that I just described, that is target divided by minimum. So yeah, and yeah, because of this early pruning condition, we will like that will be like beneficial to reduce some edge cases. So the first step can be to sort this array. The second step will be we can define a return array and a, so yeah, finally we can describe a DFS. We can take index and sum. So if sum is equal to target, then return array dot append we can make a new this one, right, a new like copy of candidates array, and then we can just return this, and then here we can so basically the idea is that if candidates I plus sum is greater than target, right, in this scenario this can be the early pruning condition. Otherwise we can have candidates array dot append we can call a depth first search over here. We can again, so we are always going to call the index that we are going to call is going to be the initial index itself, and then the sum can be yeah, so this is going to be I actually, right, because essentially index is the current index that we are at, I is the index that we are traversing, and then finally we can do candidates array dot pop, right. So in this way like finally what we are doing is finally we are popping the element, and then we can return yeah. So we have to first call DFS at index 0 and sum 0. So the reason why we are doing this traversal this way and we are only calling this at I is because we don't want repeated solutions. Like here you can see that we have 2 3, right, so 2 to 3 is a solution, but at the same time 3 to 2 is also a solution, and 2 3 2 is also a solution. So we can, if we only maintain like if we only maintain like a forward, like a loop in which we only traverse the current index and the index forward, we will avoid having repeated solutions. So let's try to submit this. Yeah, and then it's working fine. This has 43 milliseconds of runtime.